Okay, it's John Williams again from MIT, and we're talking about blockchain. And last time we talked about how the blocks were linked together by the hashes and the proof of work that made these hashes start with a certain number of leading zeros. So here's another diagram showing blocks 51, and then block 52 is linked back to 51, has that hash with zeros included in its own hash, and then block 53. So let's take a look at exactly how we communicate with the blockchains. And these are the Ethereum nodes, and you see that it would be tough for one country to shut down Ethereum because it's spread across so many countries. We're missing Asia here and Japan and lots of others, but you get an idea of the number of Ethereum nodes around the world. And each of these has a copy of the blockchain. The tricky part, if you like, is keeping these blockchains synchronized in that they all have to be the same. So when the next block is added, all of these need to agree on that block and make sure that it's exactly the same for all the blockchains. So let's take a look to see how this happens. When we launch a transaction, we're actually talking to one node of the many blockchain nodes. So let's take the case of Ethereum. Here on the left, I'm showing that we have a transaction. So Alice sends Bob 1 Ether. And now we want to get that transaction into the blockchain. So we communicate that to one of the nodes. In my case, I use MetaMask, and so I'm talking to the MetaMask node. Now that node broadcasts out that transaction to all the miners. So now the miners have pools of transactions, and they take a subset of that pool and do a proof of work and mine it into a block. We need to realize that the miners don't all mine the same transactions. They mine different ones, and all the time they're getting messages saying, here's another transaction to include in your blocks. So now we see what the miners do. The miners choose a subset of the transactions. So here I'm indicating there's a green subset, and there's a brownish orange, and there's a gray one. And now the miners mine away and try and solve the puzzle. And in this case, one of the miners says, I've solved the blue block of transactions, and sends out that solution now to all the other miners, and it gets rebroadcast. So each miner has a subset of the network that it communicates with, maybe 100 or 200 machines, and then those machines rebroadcast. So the whole network is flooded with these messages bouncing back and forth about transactions and about which blocks to add. You'll often see this kind of diagram of the whole workflow, that Alice wants to send a Bitcoin to Bob, transaction is mined, sent to the miners mine the blue one is checked by all the other miners, and if it's correct, it's added into their copy of the blockchain. Now here I'm showing two blockchains, there are thousands. So that's the thing to realize, is it's not a blockchain, it's thousands of blockchains that happen to be synchronized. Here's a different diagram, and it's showing mining pools. So the big mining pools have about 14% of all the miners, each one. There's quite a few dominant players in this. Now let's see what happens when one of the pools mines a blue block, and a few seconds later another one mines block 81 as a green block, including different transactions. Both are valid blocks, but now the question is, which version of 81 is going to be added? So they broadcast out to their networks, and the top two get the blue block first. They check it and they say, yep, it's correct. I'm going to put it in my network. The third one down and the fourth one down here from the top, they get both the blue and the green blocks. Now they've got some confusion. They're not sure which to add. So now there's a kind of a rule that says, well, you either add the one that you get first, or you add the one that has the most transactions in it, the most valuable, if you like. And so they know there's a possible conflict. The two at the bottom haven't got the blue block yet. They've only got the green block, so they add the green block. So now the question is, what happens to these? Well, they happen to choose the blue block. Now, all of these people will by this time will know that there's a possible fork, that some of the blockchains will have green block as 81 and some will have the blue. They get worried that they've got the wrong one, that most of the people in this case have got the blue one, and the green ones need to be worried because if they keep mining and add on to this green 81 with block 82, at some stage they may have to go back and put in the blue blocks, etc. They're aware of it and they're listening for messages, and as soon as block 82 now comes along, it becomes clear which block it's connected to. The 82 probably will be connected to the blue block, and so the green guys now, they got to throw that block away, put the blue block in, and add in block 82. That's how a fork occurs, and they're quite common. Here's a snapshot of the actual Ethereum network, where at this time block, the bottom block here, 2466251, has two possible blocks being added to it, the one on the left and the one on the right. Now the one on the left was mined 6 seconds before the one on the right, 204114 as opposed to 204120. And it happened that the left-hand one was added by most of the miners, and this becomes an orphan block. And the transactions in that block now need to be thrown back into the pool. We need to check that some of them will have been included in this left-hand block, and so we have to do some sorting. All the miners have to sort out what transactions to throw away, which ones are valid and still need to be mined. So that's kind of how the blockchain works. There's some issues that you need to be aware of. One is the Ethereum wallet, for example. It keeps the balance. So this is your address. This will be your public key. So people can send Ether to your public key. Your private key, if you make a transaction sending Ether to somebody else, you need to use your private key to sign that transaction. So people know who the money's coming from and who it's going to. You can't really talk to the blockchain other than by transactions or smart contracts, which are another kind of transaction. The blockchain itself writes logs, and you can monitor those logs as to the state of the blockchain. Typically, if you're going to talk to a blockchain or to a test blockchain, here you'll use somebody like MetaMask. You'll have a browser and you'll make transaction calls, for example, to the blockchain, and you're talking to one of the nodes in the blockchain. So smart contracts, you'll often see this with a smart contract. You'll often see a smart contract like this. When a triggering event like an expiration date occurs, the contract executes itself according to the coded terms. Sounds like a nice smart contract. The problem is code in a smart contract. So here's a smart contract and it has some code in it. This code only runs at the initial transaction or when another transaction references this code. So it's not like this code is running all the time, because this code is put into the thousands of blockchains. Every one of those blockchains would be running this code all the time. So that's not possible. So the only time the code runs is when a transaction comes in and is mined and put into the blockchain, and that blockchain refers to the code, maybe calling one of the functions. So there's a lot of misconceptions on the web about what a blockchain can and can't do. You'll often see this. Here's the blockchain, the Ethereum blockchain, and somehow it's watching what's going on in the outside world, looking at the outside world for events. That's not the way it works. Because really it's thousands of blockchains looking out at the outside world. And if individually they saw slightly different things in the outside world, then the blockchains would become unsynchronized. And so here's one of the questions: why can't contracts make API calls? Why can't they call out to the outside world? And the answer is because it would cause chaos if they did. So this is more the situation, that you can imagine the blockchains, lots of them, sitting behind kind of firewalls, and the only thing that's allowed are transaction messages or smart contract messages coming in to a node. And that node, as I say, rebroadcasts to the thousands of others, and they have to stay synchronized. Now, they can write events, and you can monitor those events. So here I'm showing an arrow kind of coming out. This would be a callback that when an event is put into the log of Ethereum, so Ethereum just writes these logs, that you will be notified. An event will be raised in your, say in your browser, whatever it is, that something has occurred in the blockchain. So you can be made aware of changes in the blockchain. Also, we'll need special, people are calling them oracles, that can tell us truthfully about events in the outside world. That's an issue as to what is the truth. There are some things that you can probably define as everyone agrees upon, that maybe there was over a foot of snow in the Rocky Mountains last Wednesday, or things that are more difficult to agree upon would need oracles. Okay, I'm going to stop there, but that's basically how blockchains and smart contracts work.